So the next topic in this classification lecture is about how to construct classification trees. So classification tree is a technique that splits the input space x1, x2 into different regions. And for each one of these regions, it assigns a label. So let's say that we have three classes and they are distributed in this way. So we may start by asking whether x2 is larger than a given threshold. So if it is larger than the threshold, then, or smaller than a threshold. So if it is not smaller than a threshold, then we can conclude it is a green object. If it is smaller than the threshold, we are on this side, and then we ask whether x1 is smaller or larger than the threshold. If it is smaller, then we assign the yellow label. If it is larger, then we assign the red label. So this is a non-linear model because the splits that it generates can be rather complicated, and that there is a formal definition of nonlinear, but let's keep for the moment that one. And it is a universal approximator, meaning that no matter how complex the function is, a classification tree can approximate it infinitely accurately, as long as we allow the tree to be complex enough. And for these splits, we can use categorical variables or continuous variables. For continuous variables, normally we ask whether they are larger or smaller than a threshold. And for categorical variables, we ask what is the value of that variable. And here we have an example. This is the examples of the iris flowers, where we can see, for instance, if the petal width is smaller than something, then we assign a label. This is a terminal node and we assign a label. So which label it is? We have three labels here, 0, 1 and 2, corresponding to the three flower types. And then here in this vector value, we have how many flowers of each type we have. So at the beginning we had 34, 32, 39 flowers of the same of the different types, but then those with a petal width smaller than 0.75, we see it is 3400. So that means that it is a pure population, only one type. So now we assign the label of those training samples. That would be 0. And here we are measuring something that will appear later, that is the entropy. The entropy is how variable the population is, or how pure the population is. So if the population is totally pure, we have a 0 entropy. If we have impurities, then we have an entropy value that is larger than 0. Then for those that has a petal width larger than 0.75, then we ask whether the petal length is smaller than 4.95. So we see that in this split we have decreased the entropy. So the entropy of this new group, that is composed of 0, 32, 39, is smaller than the entropy of this group that had another extra class, the one with 34. So entropy, we will give later a formal definition of it, but entropy, we can think of it as a measure of variability. So this variability is smaller than this one. So here we can choose between three classes. Here we can choose only between two classes. So the more you split, the entropy will for sure decrease. So you can see it goes from 0.99 to 0.43 and 0.17. Actually, the addition of the entropies of the children do not have to add up to the entropy of the parent. So yeah, so the entropy decreases all the time, and and at every node we make a question uh, whether a particular value is smaller or larger than something, or whether a categorical value takes particular value. And then by these splits, we are splitting or partitioning the input space into different areas, and for each one of these areas we assign a label. We have already seen this split, so petal width 0.75, that is here, so this draws a line, and then if you are below this line, then you're assigned class 0, that we have represented in red here, and if you are above the line, then you are further subdivided by these other nodes. And if we carefully follow each one of these splits, at the end what we have is this kind of space partition. Okay, so let's take another example. So we generate the data with x1, x2, x3. So they will have 4 attributes, and the main ones to define the classes. We will have 2 classes, whether these points are inside or outside this pyramid, and then there is a 4th variable that is not related to this split. So the pyramid is defined in the x1, x2, x3 space, and x4 is just pure noise. And here is the way to generate that pyramid. Okay, so now if we look at the different projections of the data, so x1, x2, we don't see the pyramid so well. x3, x2, we see one of the sides of the pyramid, the same for x1, x3, and in x4, here is x4, here is x3, we don't see any particular pattern. So that means that x4 is not, well, doesn't need necessarily to mean that, because here in the x1, x2 we also don't see a pattern, but yeah, we know because we have generated the data that x4 doesn't play any role in this classification. So here what we have is a representation of 2000 points that are classified, and then we have separated the 2000 points or 3000 points in 2000 for training, 1000 for test, and for the training we have made a number of splits. So you see x3 is smaller than something, x1 is smaller than something, and none of the splits is related to x4, because x4 doesn't play in the role in the classification. It is just a random noise variable, and then in this representation we are given how many samples are how many samples we have for the training. So the training at the beginning we had 2000, and then after this split we have 885 and 1115 and so on, and then the same for the test set. So what is the proportion of data from the test set? So we have 1000 here, 461, 539 and so on. Okay, so here we see the kind of splits that we are having. So the first split is, or one of the splits is x3 smaller than 53. So x3 smaller than 53 will assign, will further subdivide for the, if it is larger than 53, then it will not further subdivide, and it will assign directly an outside label. So we see that this corner of the pyramid will be misclassified by this label, by this assignment. How much is it misclassified? it is 96%. So 96% of the correct classification will be 96%. Okay, so the second split is whether x1 is smaller than 8. So this is this split here, and then we are partitioning the x1, x2, x3 space by these planes that are parallel to one of the coordinate axis planes, and then for every partition we decide whether to further partitionate it or to directly assign a label. Okay, so we have to devise an algorithm that partitionates the space into different pieces. So we start with something with all the samples, and then we split this set into two parts. One is already pure, the other one is not pure, and then we can further split them and take decisions at every node. So once a node is sufficiently pure, so for instance this one is completely pure, this is almost pure because there is only one sample that doesn't fit the other. So we have to decide when a node is pure enough so that we don't want to keep on subdividing it. So and for that we can use the entropy. So the entropy is defined in this way. So we have a number of classes, class 1, class 2, class 3, and then at a particular node we have a proportion of class distributions. So for instance here we have in this node I think it is more easily shown in here. So at every node we have a distribution of the samples. So we have 34, 32, 39, but here we have 34, 0, 0. So we can measure the entropy of this node, we can measure the entropy of this node. So the entropy of a node is this calculation here. So for a particular node we can estimate what is the local distribution of the classes. So for instance in the case of 34, 0, 0 would be it would be 1, 0, 0, meaning that 100% of the classes of the objects belongs to class 1, 0% to class 0, to class 2, and 0% to class 3. So now we have this 1, 0, 0, and then we add for all the classes, we add this calculation, that is, so it will be 1 logarithm in base 2 of 1 plus 0 the logarithm in base 2 of 0 plus 0 the logarithm in base 2 of 0. By convention logarithm of 0 is minus infinity, but by convention when doing these calculations 0 times infinity is 0. Okay, so we can calculate this sum, and then the entropy is the negative of that sum. And so we know how to calculate the entropy of this node. The entropy of this node, they have almost similar values. So for simplicity, let's say that the distribution of the classes is 1/3, 1/3, 1/3. So it would be 1/3 over the logarithm of in base 2 of 1/3 3 times, and then we add all those values and we compute the negative of that. So actually the maximum entropy is obtained when all the classes within a node are equally likely. So here we have a representation of the probability of the entropy as a function of the probability, and So this is the entropy of a node, and then our algorithm, what we'll do is for every node, we if the node we will try to select the best split. So if the best split, so we will try different x1s, x2 larger than something, and then for every split we evaluate what is the what is the entropy of the children compared to the entropy of the parent. And then we will see it later, just in a minute. And then we choose the best split. And if we cannot find the best split, then we don't expand that node and we make it a terminal node. You may note that a terminal node doesn't need to be pure of a pure class. So for instance, this one, we will not further split it, but it is not a pure node. So there is a small mixture of class 2 with objects of class 3. Okay, so how to define what is the best split? So this is the entropy of the parent. So we have a node with a particular mixture, and then for all the children we can measure what is the entropy of those children. So this is the entropy age of the children, and then we have to weight those entropies by the size of the children. So if one of the child nodes is very small, so that means that the probability of any of these elements falling in this child is small, then we don't care whether this child node is very pure or not, because the probability of falling in that node is so small that it contributes very little to the overall entropy. So it is, we compare the entropy of the parent compared to the entropy of the children, each one taking into account how much share of the parent observations they are taking. So this is actually a mean. This is an average of the entropy of the children. So we compare the entropy of the parent to the entropy of the children, and the split that gives the maximum entropy decrease is the one that that is the best split. So here we have an example. So let's say that we have 24 observations at this node, and 13 are of class C1, 11 are of class C2 at the parent node, and then we are evaluating different splits. So we have the split 1, the split 2, the split 3. So let's evaluate the split 2. So in the split 2, 14 of these elements go to the first child, and 10 go to the second child. And the purity or the distribution of elements within this class is 11 over 14 or 3 over 14. So that means that, for instance, here we have 11 blue points and 3 squares. So that is why we have 11 and 3. And here we have 2 and 8. So now we have these distributions that we need for the evaluation of the entropy. So each one of the children can be evaluated with this 11 over 14, 3 over 14, 2 over 10, 8 over 10. And then using these probabilities we can compute the average of the entropy reduction. So we have the entropy of the parent and then the average of the entropies of each one of the children. And if we have three candidates, so we have shown how to calculate the entropy reduction for S2, but we can do the same for S1 and S3. So here actually you have the calculations for the one of S2, and you can do by hand and check that you get the same numbers, and then you would choose which is the best split. But then there is another question: when to stop splitting? So a possible criterion is when the entropy of a node is smaller than a threshold. So you specify what is your minimum entropy, and then for this minimum entropy, once you have reached that minimum entropy, you stop subdividing. So for instance here we have the subdivisions when we have a minimum entropy of 0.75, and here when the minimum entropy is 0.3. So with 0.3 we have a lower minimum, so we have a lower threshold, so this node would be further subdivided, and then we can see the further subdivision, and it is a more complicated tree. And if we compare, well, if we calculate what is the probability of correct classification in the training and test set, this tree has 96 and 97, and this one for the further subdivided tree it is 98, 97. So in terms of the test there is no change. In terms of the training there's a very small change. So we should prefer this simpler tree as compared to the more complex tree. Okay, so here is some note on this Behenkel representation that we may represent the trees with simply the decisions that we take at each one of the subdivisions, or we can represent the subdivisions like the decisions we take here, but then we also somehow put in colors and in areas the composition of the nodes, and we say how large that is, so how we can visually see what is the purity of each one of the nodes there. Okay, so let's make an example. So let's say that we have three classes like the ones represented here. We have relatively few data, and then the first step we will do is to separate this data into 70% for training, 30% for testing, and then in this 70-30% subdivision we see that we keep more or less the same structure of data, so this is very important. And then we construct a full classification tree. Classification tree meaning that it is very complex. Here you have the MATLAB code to do that, and then what we can see is that for instance in this area we have an overly complicated tree where we have very kind of strange assignments simply to fulfill the training data. So we can see what is the confusion matrix for the training data and for the test data. And for the training data we have 0% of errors, while for the test data we have an 11% of errors. There is a huge difference between these two values, so that means that this 0% is probably an overfitted, not probably, but very, it is an overfitted model, and we have already seen it here that it constructs very strange areas just to fulfill the input data. Okay, so now we calculate a simpler tree with just 15 nodes, And so this 15 nodes tree is a subgraph of the original more complex tree. So the more complex tree, that is this one, we prune all these branches down here, and then we keep a simpler classification tree. And that is done through the MATLAB function prune, and then we have to say how many levels to prune, and somehow these levels are translated into number of branches that are to be deleted. So now the training classification error is 6, the test classification error is 11. So now it is not that clear whether this is the best we can have, and here we have an even more extreme simplification. So we have the prune level 6, so we only keep the first subdivision, and this is the split of the partition of the input space that we are inducing, and then we have a 34 or 35% of error in the training, 37 in the test. So this is way too incorrect. So we can this classification is not really good. Okay, so what we have learned is that depending on the pruning level, we have different classification errors. So this was this is no classification at all. This is the only one split that we saw just here. So the classification error is around 35%, and here is for the rest of pruning levels. So what we learned is that at the beginning these two were too different, and then at some point they get closer and closer and they are not different anymore, but then they are not good models because the classification error is too high. So we need to choose a point that is a good balance between not having a too complex model that is very much overfitted to the training data, and not having a too bad model that actually is not very helpful in the classification. And this pruning level 4 seems to be a good compromise between the two. And here we have the tree with just the prune level 4. So we see it is a relatively simple tree, and the classification error for the training and test data sets are in both cases around 9, and the surface or the partition that we make of the input space is relatively well understood and simple. Okay, so now let's take the same example but with much more data, and we see that in this area is very difficult to classify because we have very intermixed data points. So we have green points in this area where most of them are red, and the same here. So we have red points in this area where most of them are green. Okay, so this is the partition if we do overfitting, and then we see all these kind of funny shapes, and if we don't do any useful model, our classification error is around 65%. This is with a very simple classification tree, and then we have to look for an optimum. So the optimum in this case seems to be around here, 13. So for the prune level 13, this is the classification we are having, and this is a bit more complex than the one that we had before. So we see that with more data we can afford more complex models without doing overfitting. So the more data you have, the more accurate you will be able to construct your classification trees. And then here is the classification error that we see that there are almost the same in both training and test sets. And that would be all. So see you next time.